In this example of a framework, we're going to take you through how to, first of all, draw a free body diagram. Then we're going to show you how this structure is statically determinate by counting your M, R, and J. Then we're going to calculate the reaction forces. Then we're going to solve for member forces. But careful, in this one, we're not going to do the entire structure. We're going to do members AG, AB, BC, BG, CG, and GH. By doing these members, we only need to analyse joints A, B, and G. First, we're going to start by drawing our free body diagram. Here we're going to draw the structure again, the joints and the members. Drawing all the joints, draw in all the members. Remember, it's only a sketch. Going to apply the loads, the 30 kilonewtons and the 70 kilonewtons. The fixed support at B gets replaced by two reaction forces, BB and HB. The rotor support at point E gets replaced by one reaction force. We'll label that VE. Next part is to prove that our structure is statically determinate. And for that, we know that our M plus R must equal 2J. So the number of members plus the number of reaction forces must equal 2 times the number of joints. So from our free body diagram, the number of members is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Number of reaction forces we have are, we have 1, 2, 3 reaction forces. Number of joints we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. M plus R is 17 plus 3 gives you 20. 2 times J is 2 times 10. That also gives you 20. So 20 is equal to 20. Therefore, M plus R equals 2J. Hence, the structure is statically determinate, and we can use the resolution of joints method to solve for the member forces. Now we're going to calculate the reaction forces. These are going to be HB, VB, and VE. To do that, we consider the three equations for equilibrium First one of these is sigma Fx equals 0. All the forces in the x direction must add up to give you 0 for equilibrium. Looking at our free body diagram, there is only one horizontal force, HB. It's pointing to the right. It's positive. For equilibrium, must be 0. Therefore, our HB must be a value of 0. Consider the next equation for equilibrium. All the forces in the y direction must add up to give you 0. And we have two vertical reaction forces, VB and VE, acting upwards, and two forces acting downwards, the 30 kilonewtons and the 70 kilonewtons. As an equation, plus VB plus VE minus 30 because it's acting down, minus 70 because it's acting down. For equilibrium, all these must add up to give you 0. Rearrange the equation. You get VB plus VE must add up to give you 100 kilonewtons. And then to apply the last equation for statics is all the moments about any point must add up to give you 0. Remember, the moments are a force by a distance, and we must state which point we're taking moments about. In this case, we're going to take moments about our first support, which is labelled point B. Going back to the freed body diagram, point B, looking at the forces we have and the distances involved. So HB and VB act at point B, their offset distance is 0, so therefore won't produce a moment. For the 30 kilonewtons, the distance from point B is a distance across of 4 meters. The overall height of the structure from the very initial diagram is 5 meters. What else produces a moment is the force VE, and the distance across from B to point E will be 4 plus 4 plus 4, that'll be 12 meters. And then the last thing that produces a moment is the force at point F, which is the 70 kilonewtons, and the distance across from B to point F is 16 meters. Writing these down in our moment equation, we have the 30 kilonewtons, distance away to it was 4 meters. We had the reaction VE, distance to it was 12, and the 70 kilonewtons and the distance across to it was 16 meters. All these moments must add up to give you 0. We'll now go back to our free body diagram to consider which are clockwise and anti-clockwise moments. Imagine each of the forces in turn are on an imaginary piece of string. You're holding the string at point B. Considering the first load of 30 kilonewtons, if it were allowed to freely rotate, how would it rotate around point A? It will rotate around in an anti-clockwise direction, and therefore is a negative moment. Considering force VE, again an imaginary piece of string, you hold the piece of string at point B, VE is on the end of the piece of string. How would it rotate around point B? It would want to rotate in an anti-clockwise direction, negative moment. Then finally the 70 kilonewtons at point F, again imaginary piece of string, holding it at point B, the force 70 is on the end of it, allowed you freely rotate. How would the 70 kilonewtons rotate around point B? It would actually want to rotate around in a clockwise direction, and therefore is a positive moment. Updating these signs into our moment equation, the 30 kilonewtons, that was negative. Force, the reaction force VE, that was another negative moment. The 70 kilonewtons on the end, that was a positive moment. Working this through, we now have minus 120 minus 12 VE plus 1120 equals 0. Combine the numbers together and move the 12 VE to our side, making it positive on the right hand side. We get 1000 is equal to 12 VE, then VE is equal to 1000 divided by 12. VE is 83.33 kilonewtons. Now, using the previous equilibrium equation, VB plus VE equals 100, we can substitute in our value for VE, the 83.33, and rearrange our equation. VB is equal to 100 minus 83.33, and we get VB to be 16.67 kilonewtons. So in summary, our reaction forces HB are 0, VB is 16.67 kilonewtons, and VE is 83.33 kilonewtons. Now, to work out the first of our member forces, I'm going to draw a pair of arrows onto each member representing tension, and for tension the two arrows point towards each other. So I'm going to draw this onto every member in our framework. And before we start doing the analysis of our first joint, we need to work out an internal angle. For this, we're going to draw one of the members. For each of the distances horizontally is 4 meters. The height is 5 meters, and we're going to use a little bit of trig to work out and before we start to analyze our first joint, we're going to work out one of the internal angles within the framework. Each of the bays is 4 meters and horizontally, the height being 5 meters. Using a little bit of trig, we know that this is the opposite, the adjacent. So the tan of an angle is equal to this length of the opposite divided by the adjacent. Tan of our angle is equal to 5 divided by 4 our angle is equal to the inverse tan of 5 over 4, and it gives us our angle to be 51.34 degrees. Now we're going to look at our first joint. Going back to our free body diagram, we're going to highlight the forces occurring at joint A. I'm going to draw a free body diagram of joint A with our angle. So the forces at joint A look like this. We have force AB acting horizontally, and then force AG at an angle of 51.34 degrees, and our applied load of 30 kilonewtons acting downwards. Now we're going to resolve the forces vertically and then horizontally at this joint, because the equilibrium applies at this joint. So considering the forces in the vertical direction, remember when we have a force at an angle, relative to the horizontal, the vertical component will be F times the sine of the angle, and the horizontal component will be F times the cos of the angle. Resolving the forces at joint A vertically, we then have force AG. It's acting upwards, therefore it's positive, but we've got to resolve it. So we're going to use the sine of our angle. Remember, use the angle relative to the horizontal. Then we take off our 30 because that's acting downwards. For equilibrium, they must add together to give you 0. Rearrange our equation. FAG is equal to 30 divided by sine 51.34 degrees, and that will give you a value of FAG to be 38.42 kilonewtons. Now doing the horizontal resolve at the same joint, we have force AB acting to the right, therefore it's positive, plus this time force AG acting horizontally, therefore we're going to use the cos of our angle. They must add together to give you 0 for equilibrium. Substitute our value in of 38.42. FAB plus 24 equals 0. Rearrange it. FAB is a value of minus 24 kilonewtons, the minus sign indicating that it's a compression force rather than a tensile force. The next joint we're going to look at is going to be joint B. Looking back at our freed body diagram, we're going to draw a free body diagram of joint B and the forces that are occurring at that joint. I've highlighted it. I'm going to draw a separate free body diagram, and it should look like member forces acting away as per the green arrows, and we have our reaction forces applied at the joint. HB we know to be 0, VB is 16.67 kilonewtons, and our member forces are force BC, force BG, and force AB. Resolving the forces vertically at this joint, we have force BG acting upwards plus force BB. For equilibrium, they must add up to give you 0. Fill in our value for VB and rearrange our equation. Force BG is a value of minus 16.67 kilonewtons. Similarly, doing the horizontal resolve, we have minus force AB acting backwards to the left, plus HB plus force BC. For equilibrium, they will almost add up to give you 0. HB we know to be a value of 0. Force AB, we have already worked that out to be a negative 24, so careful about the two negative signs, making it positive. Plus force BC equals 0. Minus 24 makes it positive 24, but then take a 24 over the equal sign makes it back negative. So force BC is equal to minus 24 kilonewtons. Now to do our last joint, we're going to look at joint G. We were only tasked with working out the forces in certain members. So for this, we only needed to do joints A, B, and G. So now looking at our last joint, joint G, we're going to similarly draw the free body diagram for joint G and work out the remaining force members that we need. Normally the force in GH and the force in member CG. The free body diagram looks like this. The member forces are F, GH, FCG, FBG, and FAG. So when we're trying to put in some angles into this, we always use the angles relative to the horizontal. From simple triangles, the angle in the triangle shown is 51.34 degrees, and using a little bit of geometry, this angle will also be 51.34 degrees, and similarly here 51.34 degrees. We always use the angle relative to the horizontal to resolve our forces. Now doing the vertical and horizontal resolve on this joint. All the forces are acting downwards. Some of them are partially acting downwards. So we've got minus force AG. It has to be split, so we're going to take the sine of the angle, 51.34, minus force BG, because it's acting solely downwards, and similarly force CG, it's acting partially downwards, so we have to use the sine of the second 51.34 degrees. For equilibrium, they must all add up to give you 0. Fill in the values we know. FAG 38.42, BG, careful, it's minus 16.67, so two minus signs will make a positive. Then finally minus 4 CG times the sine of 51.34 degrees. For equilibrium, they must add up to give you 0. So what do we have? We have minus 30.00 plus 16.67 is equal to force CG times the sine of 51.34 degrees. When you move it over, it becomes positive. Simplify down further, minus 14.17. Divide that by the sine of 51.34. That gives you force CG, which is a value of minus 17.07 kilonewtons. Now similarly doing the horizontal resolve. Force GH plus force CG, because it's acting to the right, times the cos of the angle, 51.34 degrees, and force AG is acting to the left, therefore it's negative, and it will be times the cos of the angle, again 51.34 degrees. For equilibrium, these must add up to give you 0. FGH fill our value in for CG, minus 17.08 times the cos 51.34, and force AG 38.42. Simplify down further. Force GH minus 10.67 minus 24.00 equals 0. Combine the two numbers together, move it to the other side of the equal sign, make it a positive, and we get a value of 34.67 kilonewtons.